Okay, just one. Okay.
Yep.
Yeah, so today we'll briefly talk about where you can find all the physics tools, and mostly I will be talking about SetReplace, and I will briefly explain what local multi-way systems are. And I think in the next talk, Jonathan will talk about multi-way system and maybe other resource functions. So, okay, so I will be talking about four main things today. So first is, again, as I just said, where you can find these different functions. And in particular, I will tell you how to use SetReplace functions like WolframModel and WolframModel plot directly without resource functions. And then I will tell you about how SetReplace work internally a little bit. And it's somewhat different ways to look at, it's a somewhat different way to look at WolframModel than what you're probably familiar with. And then I will talk a bit about various features of WolframModel and WolframModel plot and where you can find documentation. And then finally, I will tell you about the new feature which was just released yesterday, which are local multi-way systems. Okay, so first of all, there are two ways you can find Wolfram physics functions. The first one is Wolfram function repository. And there is this page you can get to from the Wolfram physics website by clicking on tools. And it lists almost all resource functions we have, except maybe some very recent ones. And there are a lot of good stuff here. So I encourage you to take a look at these functions. And it's usually better to use an existing function rather than implementing something yourself. So take a look and know what these functions do. And one thing to keep in mind that these functions are not quite as polished as, for example, built-in functions in the Wolfram language. So for example, they would generally not tell you if you use incorrect arguments and so on. So just be vigilant when you're using them and use common sense that the outputs make sense. Okay, and there are WolframModel and WolframModel plot here as well. And these resource functions are just wrappers around SetReplace. And in fact, it's, in my opinion, it's much easier to use them from SetReplace directly, and I will tell you how to do that. So just some examples of functions you can find there are things like multi-way system, which I think Jonathan will talk more about in the next tools talk. And then you can, for example, generate a random Wolfram model rule. You can enumerate Wolfram models. And then one cool thing, which I don't think is in this list yet, is quantum to multi-way system, which is a function Jonathan made recently, which allows you to take a operator and a quantum operator and the basis, and then make a multi-way system based on strings, which emulates that system. So encourage you to check it out as well. And then SetReplace, so the three main functions it has are WolframModel, WolframModel evolution object, which is what WolframModel produces as an output, and then WolframModel plot, which allows you to plot WolframModel states. And there are some other helper functions and utility functions you can find in the documentation. And then the code for SetReplace lives in this GitHub repository, which if you're going to be working on features of the evolution, for example, you might want to work on this code and modify it and so on, submit pull requests. And if you want to do it, tell me so that I can add you to this repository. But one thing I want to point out is that it has a very large README with lots of examples and explaining what different properties are and which options you can supply to every function. So if you're working with some features of WolframModel, I recommend you to take a look at this. Okay, so now you can use SetReplace functions through function repository, and it generally works fine, but there are limitations. So for example, it doesn't work very well without internet connections between restarts of the kernel. And then it's a bit slower, and then you don't get syntax of the completion with it. So what I encourage you to do, and especially if you have slides open, I encourage you to do it right now, is to evaluate this packlet install command, which would install the most recent packlet. And in the future, you can generally just say packlet install SetReplace, which you download it from Wolfram's packlet server. But it doesn't quite do it yet because this new version that was released yesterday is not there yet. So, but you can still install it directly from the GitHub releases page. And in the future, if you open this releases page, every time there are significant changes, it would make a new release and you can see what's new. So you can keep following it even after the summer school. Okay, and then after you installed it, you just do get SetReplace, which is this less and less. It's a syntactic sugar for the get command, and then backtick at the end, and then you can just use all these functions like if they were system functions. So for example, you can, do all the normal stuff. And one cool feature you get with this is syntax auto-completion. So for example, once you want to specify a property in WolframModel, now you get this list of all available properties. And especially if you're not very familiar with the code, it makes it much easier to use it. And then if you want to modify the code in SetReplace, it's fairly easy to do as well. And what you'll need to do is to clone the repository and then go to the SetReplace directory. And there are build script and install script. So you call the build script first. And if you're on Linux, it will probably work right away. So you need to have Wolfram script installed. But if you do, it would probably work right away on Linux. On the Mac, you will need Xcode or command line tools. And on Windows, you will have to install a compiler. And it's a bit more complicated there. But if you need any help with compiling it, just Slack me and I will help you to do it. Okay. So let me then explain how SetReplace works. So SetReplace works with a slight generalization of WolframModel, which are set substitution systems. And basically it's just a system that substitute subset from a set with another subset. So, and we start with a set of expressions, and set it's assumed it's unordered, so just an ordered collection of expressions. And then there is a rule which says take some number of expressions from this set and replace it with another subset. And in fact, since version 12.1, there is a build function that can do it. So it's called subset replace, and you can just take a list or set of expressions and you can apply a rule to them. And you see it replaces 1, 2 with a 3, and then 5 and 6 with 11, and this 3 is left by itself. And you can do exactly the same thing with WolframModel. It's just when you specify the rules, you need to say pattern rules and put it in an association. And then that's a rule which is similar to the rule here. And then the initial state goes here. And then to get the actual expressions, the set of expressions as a result, you request a property called the final state. And you get exactly the same result. So you might wonder, why would you even want to use WolframModel if you already have subset replace? So the reason is that WolframModel has a lot of functionality to make it easier to analyze the systems. In particular, if you just call it without any property, it gives you this WolframModel evolution object. And then you can ask a lot of things from it, not just the final state. For example, there is a property called expressions events graph, which should give you this visualization of what the system actually does. And here you can see we have 1, 2 is an inputs, and yeah, so the light blue vertices correspond to expressions, the elements of the set, and then the orange vertices correspond to events. So here, for example, there are 2 events, and they take 1, 2 and give you 3, and then 5, 6 and give you 11. And this 3 is never used. So it's it's useful to see what's happening in the system. So now, what does it have to do with Wolfram models? So in the Wolfram model, expressions ordered lists of atoms, and atoms are just some, anything atomic. They don't have internal structure, they're just labels. And atoms are hypergraph vertices, and expressions are hypergraph edges or hyperedges. And each expression of hyperedge is ordered within itself, and then the entire thing is unordered again. And in order to make a Wolfram model rule, you do it in this way. So on the left-hand side, we now have two triplets of atoms or two ternary edges. And then this V2 is shared between them, which means it has to appear in both of those edges at these particular positions. And then on the right, we have a module. And what module does is that it creates a new name for this variable V6. And then it puts this in the edges on the right-hand side. And to demonstrate it more clearly, we could just run module by itself. And so you can see if you don't assign anything to V6, it just escapes and you get this random name as an output. And this is kind of what WolframModel will do in this case. So you can use this rule as a pattern rule, and you just get the evolution of the Wolfram model as you would normally. But it's kind of inconvenient to keep writing module and patterns all the time everywhere. So there is just syntactic sugar to simplify it. And what you do is just you drop patterns on the left and you drop the module on the right, and it knows which vertex is new because it doesn't appear on the left, it only appears on the right. And then you get this simplified notation for it. And you can even drop the V's and just leave the numbers, in which case all you get is just a normal way of specifying Wolfram models. And you can always go back to this full pattern specification by using two pattern rules function, which should give exactly the same things here. Okay, so throughout this talk, I will be using this vocabulary, which is slightly different from a normal one, but I think it's easier to use it because, for example, if you're talking about expression events graph, there are edges in this graph between expressions and events, which are not hyperedges. So if we use the word edge there, then it's not clear whether we are talking about edges in that graph or the hyperedges, and it gets confusing. So essentially, the expression is an element in this unordered set, or in other words, a hyperedge. Then the atom is a part of that expression or vertex. And then the set is a state of the system of the hypergraph. And then the rule, well, you know what the rule is. And then there are events and matches. And the difference between them is that event is an application of the rule that was instantiated, whereas a match is an application of a rule that is possible, but it has not been instantiated, either not yet or because there is an event selection function that prevents it from happening. Okay. So now another thing I want to explain is how SetReplace handles these evolutions internally. So kind of the ordinary way of thinking about Wolfram models is in terms of states. So for example, you have this rule with this initial condition and you evolve it for 4 steps. And as a result, you get the states plots list with just a list of states. And these states, well, as I'm sure you know, they don't just have one event in between them. They have events applied everywhere in non-overlapping ways, in as many places as possible. But actually, internally, SetReplace doesn't work like this. In other words, it's like you might think that all it does is that it takes a state and it applies some events and get another state, and it just remembers those states. But actually, no. What it does, it keeps track of all of the edges throughout the evolution. It has all possible matches at every point, and then it remembers all the events it applied. And in fact, if you look at the internal structure of the Wolfram evolution object, which I will talk in more detail about later, you can see that there are no states in here. They're just atom lists, which are just list of expressions or list of hyperedges. We just has all of them in a single list. And then it just has a list of events with inputs and outputs. And again, as I mentioned previously, it only has these three things which it remembers. And this list of all expressions throughout the evolution, it's not just catenated states. It's more subtle than this, because, for example, here, it starts with 3 binary self-loops, which is the initial condition here. But the next stages here are 2, 2, 2, 1, 1, 2, and 1, 2. But there's no 1, 1 here, because it's the same 1, 1 as this 1, 1. It was just never, it was not used going from the first state to the second state. So it got preserved, and it's still the same edge. So it doesn't appear here twice. And to demonstrate how this works, actually, we can look at the expressions events graph state by state. So we start with 3 edges, 3 binary self-loops, and then we go step by step. So it first finds 2 edges that match the rule, and it creates outputs. And then it finds another 2 edges, and it creates the outputs. And by default, it never reuses edges. So once it uses it once, it doesn't use it anymore. So it only looks at expressions here without degree 0, and it keeps, it can match expressions from different layers as well, and it just keeps doing it. And note that this particular state here is in between, well, this configuration here is in between states, because this is a complete previous state because it's fixed number of layers, and it started evaluating the next layer, but it didn't finish it yet. So now it's in between the fourth, or let's see, 1, 2, 3, in between the second and the third step. Okay, so now let's talk about some specific functions or features in SetReplace. So first of all, as I mentioned previously, there is this README, and in particular, it has navigation bars at the top. So what you can do is you go to symbols and functions, for example, and then you can go to WolframModel, and then to properties. And here are all the properties. For example, you can ask from the evolution object, like causal graphs, and then you see some examples of causal graphs. And I will go through some of those parts of the README right now, and I will not, I definitely won't have time to go through all of them. So I encourage you to look at it later. Okay, so one of the functions we have there is WolframModel plot, which is what we use to plot the WolframModel states. And by default, it draws each hyperedge or each expression as a convex polygon around the corresponding vertices or atoms. So here, for example, there are 3 expressions here, 1, 2, 3, 3, 4, 5, and 5, 6, 7, 1. And I also included vertex labels to make it easy to see what's going on. So there are some edge cases here. So for example, if we have self-loops, it still does a similar thing, that it draws a convex polygon around this edge. But since the atoms in it or vertices in it are reused, it just draws a self-loop. So for example, the reason this 1, 1, 1 has 2 self-loops is because it first treats it as 2 pairs of 1. So it's 1, 1 here and 1, 1 here, and each of them correspond to 1 self-loop. And then it draws a convex polygon around the whole thing. So that's how you can see it's a ternary hyperedge and not 2 binary hyperedges. And then 3, 4, 4 is a similar thing. So there is a 3, 4, and that is a 4, 4. And then there is a convex polygon around the entire thing. And for example, if you have to distinguish between something like 1 to 1 and two edges 2, 3, and 3, 2, you can check whether it's filled inside 1 to 1 or not. And then if you have overlapping edges and so on, sometimes it can get pretty complicated, but you can still kind of see what's going on because, for example, here, the shade of blue is slightly darker and there are double edges here, which is how you can see there are two ternary edges, ternary hyperedges 3, 4, 5 here instead of 1. Then if you have unary hyperedges, they are drawn as circles around corresponding atoms with the number of vertices corresponding to the number of circles corresponding to how many unary hyperedges you have there. And then you can do other things with it. For example, you can highlight certain parts of the hypergraph, like hyperedges and vertices and so on, which is especially useful if you're writing documents. And then if you don't like the cyclic nature of the polygons, because it connects the last vertex with the first vertex, and you might not want to do it because there is, I mean, it does it to show you where individual hyperedges are. But if you don't want to do it, you can disable it by setting hyperedge rendering to subgraphs, in which case it would draw all of the hyperedges as just sequence of vertices. So if you're doing something like a subway map, for example, you wouldn't want them to be polygons, so you could just color them in different colors instead. And this option H style even supports patterns. So for example, you can say that every binary hyperedge should be dark green, but every ternary hyperedge should be dark red. And this is what you would get. Okay, so another visualization function is rule plot. And the reason you would want to use rule plot instead of Wolfram model plot for rules is that it shows you identical elements in the rule at the same places. So for example, it has 1, 2, 1, 2 on both sides. Well, it has 1 and 2 on both sides, so it puts them in the same place. And it also does it with whole hyperedges, and it also highlights them in different shade of blue so you can see which ones are shared. And it supports multiple rules as well by showing them side by side and so on. Okay, so now let's go to Wolfram model. So Wolfram model generates evolution objects by default, as I explained previously. So the way you use it is you specify rule first, then the initial condition, and then the step specification, which I'm going to talk about more on the next slide. And in this case, we just ask it to generate 8 events. And then we get this Wolfram model evolution object. So the way it works is that, so it has some internal structure and it has these little labels which can kind of let you see what's going on. So in particular, it says generations for triple.5. So what it means is there are 4 complete generations, which means that once you get to the 4 generations, which are 1, 2, 3, 4, there are no more edges, no more hyperedges that would appear on the 4th generation, meaning that it's complete. All of the new hyperedge expressions will go to the 5th generation and beyond. And then this 5 is a total number of generations, meaning that what is the deepest one that it goes to. And generations just correspond to layers in this expression events graph or alternative causal graph. So each time a new event is created, its generation is 1 more than the highest generation of its inputs. So like this edge, for example, so this expression has generation 1, this one has generation 2, and therefore this event and all of its outputs have generation 3. and so on. So then you can, as I showed previously, you can look at the internal structure of the evolution object, and it only has the first part, doesn't have any other parts in it. And this is all that's used to evaluate properties. So, so specifically, it tells you first that it's a version 2 data format, which is the new version which was introduced in the release yesterday. And then it repeats what the rules are, which it also shows here. And then again, the maximum complete generation termination reason, which just tells you which of these step limiters was triggered, and I will talk about it more later. And then atom list is the same thing as all expressions throughout evolution. And then there are some properties of events, including generations. And then to get things from the evolution object, what you do is you call different properties from it. And some properties also have options. So for example, for expressions events graph, you can specify vertex labels, roast automatic, and you can include the initial event, which is this event here. And it's just an event that takes no inputs and creates the initial condition. And of course, there are many different properties like all events count. And there is even property called properties, which gives you a list of all available properties. And as a syntactic sugar, you can also specify properties directly in WolframModel as a force argument. So for example, there is all events edges list or count, which will tell you the total number of edges or expressions throughout the evolution. Okay, now let's talk about step limiters. So these are the things you can specify as a third argument in WolframModel, which tells it how long it should be running the evolution. So the number here means the number of generations. So for example, here we ask it for 4 generations, which is what it does. And one thing to know about this number of generations is that it would not terminate the first time it have encountered the higher generation. Rather, it would just ignore the matches which have generation that is too high, and it would apply all the other matches as long as possible. And in the default evolution order, it doesn't matter because it would always produce events generation by generation. But if you use custom event ordering functions like newest edge, for example, which is essentially a depth first search, then it does matter, because what the newest edge you want to do is it wants to go as deep into the causal graph as possible. So in this particular case, it goes 1, 2, and then 3, but then it hits a limit of the number of generations, which is 3 here. So it keeps going on the other branches. And in the end, in this particular system, it actually produces the same result as a default event ordering function would do. But instead of generations, you can also specify the events count, as I demonstrated previously. And this is, in a sense, it's a simpler way to use it, because you ask for 3 events and this is what you get. And then also you can limit by the number of vertices, atoms, or expressions at the final step. So that wouldn't work for multi-way systems, but it's quite useful for single-way systems, because it would, unlike the number of generations, it would actually terminate as soon as the current state got more vertices or edges than requested. So for example, here we ask for 7 vertices and we get 7 vertices here. And the same goes for edges. And you can even combine them. I mean, you can combine any of them, including the max events and so on. And it will terminate as soon as the earliest of those is reached. Okay, so some other properties we can talk about. So the most straightforward one probably is to obtaining states at a particular step or event of the evolution. And the way you can do it is that you just give a number to the evolution object without any property string, or you can also use generation, but you don't have to because it's assumed by default. And this here, for example, gives you the state at the fourth step, or the fourth generation in the evolution. Another thing you can do is to request a state after a particular event number. So here, for example, it's state after the seventh event. Again, both of these only work for single-way systems because the ideal state is not very well defined for multi-way systems, or for local multi-way systems, which I will talk about later. But you also can come backwards, like when you do unspecified parts of expressions. So for example, here we are requesting a -2nd event, which means it's the event which is previous before the last one, when we get the state which was generated after that event. Okay, so then of course you can plot the states with Wolfram model plot in a very straightforward way, but you can also save yourself some typing and just ask for plots directly. So there is a property called final state plot, which would give you exactly that. And then you can do states plots list, which gives you plots for each step along the way. And then you can even specify Wolfram model plot options as options for this property. So for example, you can say hyperage rendering goes to subgraphs, and you get that here. Okay, so the next thing you can do is ask for events. So one of the properties is all events list, which would give you the all events. So here, the first number here is the index of the rule that was used. And because there's only one rule here, it's always 1. But in case of multiple rules, it could be something different. And then these numbers here, they are not hyperages, or they're not expressions themselves. Rather, they're indices of expressions in the all expressions list. So for example, the first event here takes 1, 2 as an input, which corresponds to this 3 self-loop ternary hyperages, and then it produces 3, 4, 5 as an output, which are these ones. And so, and one more thing you can do with events is to visualize them. And here, the property is called event states plots list, and it just gives you plots at a state after each event, not at each generation, but at each event. And then the red and dotted hyperages here highlight where those events were applied. So for example, if you look at these two states, then the gray dotted hyperages correspond to hyperages that were destroyed at the next events, meaning from this state and this state. And then the red bold hyperages correspond to edges that were created. So in some systems, I mean, it's more confusing in some systems than in others, but in some cases, it's very useful to see where the activity happens in a particular system. Okay, so the next thing we can talk about is causal graphs. So expressions events graph is a kind of causal graph which shows you not only events, but also expressions. And it's, in my view, it's actually more useful than the causal graph. And it's, again, was introduced in the release yesterday. And for example, if you have a system, and I mean, I showed some of them before, but here's another example. So if you have a system which takes 2 numbers and gives you some of those numbers, then it just shows you exactly how computation happens. Like you take 0, 9, you get 9, you get 16, 12, you get 28, and so on. So the causal graph is just a compressed version of this. So if it doesn't have vertices that correspond to expressions. It only has vertices that correspond to events. And then edges between these events correspond to causal connections between events, which correspond to paths going through expressions in this graph. So for example, there are these two events here correspond to two events here, and there is edge between them because there is a path through 11 here. So there is a property called causal graph, which just uses the default layout for the vertices. But I recommend you to use layered causal graph instead, which would put events at the correct layers corresponding to their generations. And expression events graph would automatically do that as well. So one interesting thing about causal graphs is that they will let you see quite easily what are possible evolution orders are for a system. And the way you would get different evolution orders is by considering different foliations of the causal graph. And foliation are just lines you can draw through it. So for example, here, if you draw lines at each layer in the expressions events graph, they correspond exactly to generations which are returned by states list. In particular, the first element here is just the initial state. But then the second layer has 11, 9, 16, and 12. And then the 7 here correspond to this 7, which is preserved at this state because it was never used at the first step. So, and the way you can see it's still the second state because there is an edge going through it, corresponding to it. And then you can keep doing it and you will get all of the states. But of course, in different event ordering function, those lines don't have to be straight and they can be tilted, which would correspond to different evolution order and as a consequence, a different reference frame. And you can immediately see what kind of states you can get in a given system. So one more advantage of using expressions events graph over the causal graph is that it will let you very easily see where the multi-branching happens. So for example, let's consider a system which just a system of a unary edge moving through a directed graph. So the rule just finds this unary edge and the directed edge it can go to, and it moves it to its destination. And then if you start with initial condition like this, where you can see there is two possible ways this unary particle can go to, then in a causal graph, and if you make a expressions events graph of it in a multi-way system, then it will show you that once this unary edge is at position 2, then there are two events that can be applied to it. One makes it interact with 2, 3, and one makes it interact with 2, 4. And the way you can see there's multi-branching happening is because there are two, the out degree of this expression vertex 2 is not 1. So there are different choices here. And that is something you cannot really see on the causal graph, because on a causal graph, you would just have two outgoing edges from this event, and you don't know whether it's just this event created two edges at the output, or if it's branched like it did here. Okay, so I can talk more about these features, but I think I will jump to the local multi-way systems now. I'm just going to briefly mention what these are. So include boundary events, and it works for basically all properties, and it lets you include fake initial and final events, which is what you can see here. And then methods. So there are actually two different implementations of Wolfram model. One is written in Wolfram language, and it's more generic and is usually used for pattern rules. And one is written in C++, and it's typically faster, and method lets you switch between them. And you can also use time constraint, and you can still get partial evolution objects when time constraint is reached, even if it didn't finish evaluating. So you can see termination reason time constraint here. So you have to use evolution objects to do it. If you just ask for property, it wouldn't give you that. I mean, it would just say aborted instead of say result. And then you can specify the order of events by using event ordering function. Okay, but for the multi-way systems, what you want to do is specify the event selection function. And the reason for it is that in the normal evolution, which corresponds to event ordering function, goes to global Spacelike. Every expression is only used once. It is never used, which corresponds to a way of selecting events. Means that you cannot select two events which use the same age in that kind of evolution. But by choosing different event selection functions, you can do that. So, and we only have two different cases right now, either global Spacelike or none, but chances are you'll have more pretty soon. So let's again consider a similar system as we did previously, where you have a unary edge going through a directed graph. And in this case, let's make it branch immediately and then reconverge back at vertex 4. So in a single way evolution, what will happen is that it has to make a choice either to go to 2 or to go to 3, and it can go to both of them. Because again, it cannot reuse this unary edge at position 1. So here's what happens. It picks the earliest edges here. So it goes to 2, and then it goes to 4. And the edges of expressions 1, 3, and 3, 4 are never used. But if you specify event selection function goes to none, it's going to do both of them. So it will move to 2, but it will alternatively move to 3. And you can see there are two events coming out from this edge 1. And then it keeps moving to 4 in both cases. And now we have two different branches here. And basically, so to explain again, since SetReplace doesn't really care about states, it can very easily do it because really all it has is a bucket of states, or it has buckets of expressions, and all it needs to do to produce this multi-way system is to not delete expressions after they're used. So it can just reuse them again. But to explain what does it mean for event selection function goes to none versus other kind of possible local multi-way systems, I need to explain what it means for two expressions to be spacelike, timelike, or branchlike. So in a single way evolution, expressions can be either spacelike or timelike. And that just depends on whether there's a causal connection between them or not. So for instance, here we have a single event that takes one expression and produces another expression. And these two expressions are timelike because they're causally connected. So another possibility is to have an event that produces two expressions, in which case they're spacelike because they coexist they could coexist in the same state of the singular evolution, but they're not causally related. And this keeps preserved, after multiple steps as well. So for example, here, all of these expressions at the bottom can coexist with one another in a single way evolution. So they're all spacelike with each other. But in a multi-way system, we also have another type of relationship between expressions, which is branchlike. And that happens when there are two different local branches and there are different edges in them. And those edges would be branch-like separated. And the way you can see it is that if you go to the common ancestor, if that common ancestor is an event, that means that those expressions were produced in a consistent way with one another, so space-like. But if the common ancestor is an expression, it means that this expression got matched to two different events. And that in turn means that it has to be, the separation has to be branch-like. Or in other words, there is no single way evolution in which these two expressions can coexist with one another. And what match-all system does is that it matches all groups of expressions, whether they're space-like, branch-like, or even time-like. It doesn't care about it. And which is why it's called none, because there is no selection whatsoever. It chooses all of them. And so, for example, here, these two expressions, 1 to 3 and 1 to 4, are branch-like separated because there is this expression 1, 2, which was used in both of these rules. But the match-all system still matches them, even though they are branch-like separated. And similarly, it can match time-like separated expressions as well, like you see here in this event, because you can use these two expressions, 1, 2, and 1, 2, 4, are related to one another causally, but still this event uses both of them as inputs. Okay, so the interesting thing about this local multi-way match-all system is that it actually allows interference between different branches. So if you only match space-like separated edges or space-like separated expressions, it means you can only ever get expressions that appear on the same single way evolution at the same time. But in a match-all local multi-way system, that's not the case, because, for example, here, and these rules are kind of complicated, so you don't have to look at them. So just look at the output. And here you can see that there is an event. So this first event is just a normal event which takes one expression in and produces two other expressions. But then here, this expression is an input for two different events. But they then merge because it's a match-all system, so it can merge branch-like separated expressions to each other. But then this event is again has space-like inputs because these two expressions exist on different branches. And so in a sense, it's kind of like having some quantum effects happening here, but then they just influence the classical state. It's kind of like if you do a quantum experiment somewhere, and then you get a result from this experiment on your computer, then your computer is perfectly classical object, but it's influenced by quantum effects. So this is what, it's possible that this is how it looks like. So you have some branching and merging here, which is some kind of quantum process. And then you get the event which merges them, but yeah, it just uses them as inputs and so on. Okay, and finally, let me explain the difference between global and local multi-way systems. So, and again, let's look at a similar system as we did previously with, again, unary, in this case, two unary hyperedges moving around the directed graph. And let's see what the global multi-way system, which is resource function multi-way system, would do here. So you can see the global multi-way system has states in each vertex. So and it shows them as entire plots here. So in particular, and it enumerates all possible events that can match the state and all possible sequences of these events as well. So like, for example, here, it can move either one of those particles or the other one of those particles independently. But because it does it this way, there's a lot of redundancy going on. Because, for example, if you look at these two highlighted events, they're actually the same event because they move this particle on a longer branch inwards. And this one does it as well. But they're duplicated here because the states they start from are different. And that's why you get all this grid here instead of just two paths. But local multi-way system wouldn't actually do it because it does everything locally. And so here we just get this A1, and actually let me copy this and label the vertices. Yeah, so as you can see, there is an A1 and it keeps moving here, becoming A2, A3, and then M1. And then B1 also moves inward, becoming B2 and M1. And it evolves them independently. And then they only merge at the end where they don't really merge, but they use the same hyperedge as an input, which is M1, M2. And so in the end, you just get two expressions M2, which is the same as here, but you code them more efficiently. So at the very least, the local multi-way system is an optimization for the global multi-way system. But in addition to that, it has this interesting features because it allows one to have interactions between different branches, which is an interesting thing that needs to be explored more. And I mean, since it's just released yesterday, we didn't really do much research into what really happens in those kind of systems, but it's one interesting thing to look at. Okay, and just a summary. So we have, again, these are all the links I showed previously. So the resource functions on this page. Then we have a SetReplace documentation. And I also written a little bulletin about local multi-way systems, which unfortunately doesn't use expressions events graph yet because it didn't exist at the time, but it explains what local multi-way systems are in more detail. And of course, if you have any questions of any kind, but especially about SetReplace, whether you're trying to compile it or you want to modify it or you just want to know about what particular features do, just Slack me with questions anytime, and I will be happy to answer them. So that's all I had to say. So thank you all for being here. And I'm not sure how exactly it should work now, but I think now it's time for questions.
So one thing I want to encourage people is if they don't want to ask questions directly here, they can post them in the, I guess we can use a physics, the physics channel for now. And I do have a question, Max. So what are the limitations when using these functions on like a regular computer? Like how many steps, how many evolutions can we work with without crashing the computer?
Well, so the good thing about it is that if vertex degrees are small, or alternatively speaking, if the number of matches is not significantly larger than the number of events it actually applies, then it has a linear time complexity with number of events. And you can go from there. So basically, so they're also memory constrained, but generally you can do you know, at least a couple thousands of events pretty easily, and in some systems a lot more than that.
I see. So another, well, it's more a comment than a question. So in your slides you have, just let me find the correct slide. So there's one slide you showed for people to install the Packlet directly from your repo, right? Because we don't have the Packlet yet in the public server, I think, right?
Yeah.
So I expect some people having issues with Packlets, and so maybe we can leave that for, let me see, we have the group discussion later today. Yes, to show people some of the Packlet functions. Like I see, if I try here on my machine, I think if I check I haven't installed your Packlet, but if I check the version I have is 0.3.15, and I think yours is 26 or something like that.
Yeah.
Yeah, so it will probably be useful for people to see also these Packlet functions. So in case, you know, sometimes you have issues with conflicting versions or stuff like that. So if people are going to manually install Packlets, I think we should show these kind of tools too.
Well, so, right. So when you install a Packlet, let's see. Let's see, where was it? Yeah, so when you install a, okay, can you install it again? Yeah, so when you install a Packlet, you just get a version here. You can see it, and then, well, if you have a previous version and you're trying to install a newer one, it will just get upgraded automatically. If you're trying to install older version, then it won't work by default, but you can uninstall it first and then install it again. And then, let's see. And then if you use a script to build and install manually, it will automatically delete the previous version you had, even if it was a newer one, and it will install the one you built most recently. So I don't know, does it answer the question?
Maybe that's a question for the students. I'm just trying to think that, so even from the development side, we have problems sometimes with when dealing with Packlets manually. So I expect some people having this kind of issues. So when you,
yeah, so we are not using here, we are not loading Packlets from development directories here. They're always installed. Even here, they are installed before they're used. So it's actually pretty straightforward.
and once you install the Packlet, do you always have to do the get set replace?
Yeah. Yeah, you need to restart the kernel. If you install it in this way, you have to restart your kernel first, and then you just get set replace.
I just wanted to say thank you. This was a really great presentation, and I learned a lot more about things just from the regular lectures. I did have a question.
Thanks for listening.
Yeah, thank you. I did have a question about when you constructed the foliage dotted lines.
Okay.
So
Foliation.
yeah. So when you want to create branch-like connected images just based off the foliation images, is there a different procedure to do that instead of just creating dashed lines through graphics? When you want to create those surfaces to visualize?
Well, not really. We don't have any automatic way to do it right now.
Okay.
Yeah, so I agree. It would be definitely nice to have, in particular, like for a specific evolution. we can construct foliation which would show where, how this evolution goes, but we don't have it right now.
Okay, thank you.
And also, since I think we have the group discussion later today, I guess people can download your slides and play around with those and start writing down their questions, so we can have them. We can have the answer later today. Also, can you suggest any from the technical documents in the physics website? So let me go there. Yeah. So if you go to the technical introduction, and so can you suggest any particular section here that illustrates what you show here? So to start also playing around with this.
Well, most of them use WolframModel in some way, but well, they either use WolframModel or they use a multi-way system, and especially if they look at other systems. And as far as I know, there's nothing here about the local multi-way systems.
Or like, what's the best chapter here? What's the best section to, like as a background reference to the things you are showing today? Like if people want to play with these tools during the day.
I'm not sure there's any particular section here. I mean, if you want to see examples specifically on how to use it, you should just look at README. But here, I mean, there are many examples throughout, but I cannot really point any particular section.
Or so you said your GitHub repo should be better for that?
Yeah, if you go to just GitHub repository, there is a README, which is very detailed and has a lot of examples here.
Okay.
Any other questions?
I do have oh, sorry. Go ahead.
I was going to say, I do have a comment. I yesterday this is Mark. Yesterday I downloaded a document called Hands-on Introduction to the Wolfram Physics Project. And the title of the file is Physics Tools. I might have changed that though. It's a notebook. Of course, it doesn't have the ones that were published yesterday, but that gives you something that you can actually work through and play around with. I found it very helpful.
Yeah, that's actually a good point.
Where I got this, I don't remember.
Yeah, it's here. If you go to Software Tools and then Introduction to Wolfram Physics Project Tools, then there are examples here as well. Let's see.
And can you post that link on the physics channel, please?
Right. Okay. Hold on.
Thanks.
Okay, and there are some questions I'm getting on Slack. So one question, what is the difference between an event and a generation? So event is a single application of a rule, and generation is as many applications of the rule as you can do without making them overlap. So only using each hyperedge once is as many events as you can do. That's the generation. And then what exactly is a unary edge? So a unary edge is just, let me show my screen again. Yeah, a unary edge is just an edge with a single vertex in it. So the normal binary edges have two vertices in it. If you only have one vertex, that's a unary edge. Okay, and I think I have another question in Slack. Let's see. Yeah, so what does it mean for two edges to be connected simultaneously in the causal graph? So that to see what that means, it's actually useful to look at expression events graph. So if we have an so if we have an event with multiple outputs or inputs, so for example, we can have an event that takes one edge in and then two edge out. And we can have another event which takes two edges in and one edge out. And then if we start it from something and we do as many events as we can, and we generate an expressions events graph, so you can see there are two paths through it between these two events, which correspond to two different expressions. So if we compress it to a causal graph, then they're just two edges. So two edges correspond to the fact that there are two expressions that are produced by one event and then used as inputs by another event. But in a causal graph, there are no vertices inside of them. So only thing that's left are two edges. But the fact that there are two edges here exactly corresponds to the fact that there are two paths here. So are there any other questions?
Yeah, Max, I just want to say, yeah, thank you for the talk. Me in particular, I don't really have any questions right now because I'm already fiddling around with your slides. So that's probably it's the same case for other people. So yeah. So thank you for providing like a slideshow that we can actually like mess with.
Sure, thank you.
I think also our room may kick us all out. I think we're supposed to have a group discussion. I don't know if that's supposed to be in the same room or not. We usually have to like switch between rooms.
Oh, okay. Let's see.
I don't know. Maybe either Aaron or Christian would know that.
I think let me check.
No, Aaron's not here. Yeah.
Yeah, it's in another room.
Okay, so say again, should we go to another room or how it works? How does it work?
Yeah, I think you have to move over here.
I have one last question, if we have time.
Sure.
What can you? I'm very curious about the possibilities of exploring hypergraphs in 3D, and what could you speak to about that?
Yeah, so we don't have Wolfram models 3D yet. So I was working on it at some time before, but I didn't have time to actually finish it. So there is some prototype on it in one of the branches, which I can show later, but it doesn't really work that well. But what you can do in the meantime is that to see the structure of a hypergraph, even if you, so you cannot, like, there's no way right now to draw properly the hyperedges in 3D, but you can always do the following. So you have this hyperedges, so you can turn them into binary edges first by partitioning them in this way. So here I partition each of them into parts with 2 elements each and 1 element apart. So for example, 1, 2, 8 becomes 1, 2, and 2, 8. And then we catenate them so that they are single lists instead of lists of lists. And now these are just binary edges, which means we can say directed edge on them, and I'm applying it to each of those lists. And then we can just do graph 3D, and we get a 3D graph. So it's not quite as good as Wolfram model plot because it doesn't tell you which ones are the hyperedges. It essentially, what it does is the same thing as hyperedge rendering versus subgraphs do, but it's still pretty useful to see the general, the general structure of the graph.
That looks very nice. Thank you.
Or so I had the wrong calendar. I just updated my calendar, and yeah, I see we have the group discussion now. So what we did with Jonathan was we went to that Zoom room, and you should be a host there, or maybe Erin's there, and you can
You're
make
saying I should make a breakout rooms?
Yeah, we can make the breakout rooms.
Yeah, I
we
can do that.
also with the high fidelity space before this with Jonathan's lecture, but probably here using if you are going to share the screen, Zoom will be better. So I suggest we move to that Zoom session so you can create the breakout rooms, and in the breakout rooms channel in Slack, I can create a thread for each room and people can post their questions there.
Okay. So how many people per room do you think would make sense?
You mean how do you assign people to the breakout rooms?
No, how many people per room?
How many people? I don't know. I think it depends on how many people we have here. And I think
because I can make rooms of different sizes.
I believe so, yes.
Well, okay,
And I think
let's
some
do.
people are also going there. So yeah, I think we should just move there and organize the rooms in that Zoom session.
Wait, in a different Zoom session?
Yeah, just go to the
confused.
calendar and
okay, I'll do that.
And you should get the, let me see. Yeah, group discussions, physics tools 1, and there's the,
okay.
Yeah, there's this, you just have to click the join live meeting.
Sure,
and
yeah.
directed to the Zoom session. Okay, so I'll see you
Okay.
there.